In section 10.4, our goal is to investigate rotational kinetic energy. Our objectives here are to define rotational inertia and define its role in rotational kinetic energy, and also be able to identify various forms of energy in a given system, including rotational forms, and use those energy considerations to solve problems. So first of all, let's just think about kinetic energy and what that means. Would a rotating object actually have kinetic energy? Of course, that answer is yes. Any object that has mass and is in motion is going to have kinetic energy. In the next few sections, we are going to investigate what this kinetic energy might look like for an object that is rotating and consider the work done in that rotation. So basically, we're going to end up developing a rotational version of the work kinetic energy theorem that we saw in Chapter 6. So consider a rotating object. Maybe, again, it's a CD. And you look at this CD kind of rotating around maybe in this direction. This CD is obviously a collection of particles, and any one of these particles might be something sitting over here that's rotating around this z-axis coming in and out of the page. Now maybe it's rotating around with some sort of angular speed omega, and any particle is going to have some little bit of mass. Maybe this little particle here has mass m sub I, and it's going to be moving at a speed tangent to the path with some sort of velocity. So if we were to look at the kinetic energy of any one of these little individual particles, of course we know that kinetic energy is going to be a 1/2 mv squared. So any one of these particles, or the ith particle, is going to have a kinetic energy of 1/2 mivi squared. That means that the total kinetic energy of this entire disk is going to be the sum of the kinetic energies of all the little particles of mass or pieces of this CD as they all rotate around with their own little masses and their own little velocities. So if we were to sum them all up and sum up these 1/2 mv squareds, we could use the fact that we now know the connection between a translational velocity and a rotational velocity, in that v is going to be equal to an r omega, and we can plug that in for v squared. So you can see that we squared the r and squared the omega. That's basically our v squared. The 1/2 can be pulled out of the summation because it's the same for all the little particles or bits. And now we can kind of separate out this summation of the mr squareds and also pull the omega squared outside of the summation. Now why can we take omega outside of that summation? The reason is because every single particle that is a part of this CD or this rotating object, every single one of them will be rotating with the same omega. Remember, that's one of the beauties of actually defining these rotational variables, is that every single piece of this object will be rotating with the same rotational or angular speed, which really means the only differences are the little bits of mass and where those little bits of mass are located. In fact, this chunk that we're keeping separate here in this summation is what we actually define as the moment of inertia, or the rotational inertia of the object. Rotational inertia has a symbol of a capital I and is equal to the summation of all the little masses multiplied by their positioning or their radius squared. Now notice that this depends not only on mass, but also on the distribution of that mass around the axis. So essentially what we're saying is that something that has a lot of mass that is located far away from the axis of rotation is going to have a very large moment of inertia. This really is looking at how difficult it is to start or stop this thing rotating. It's really a measure of the object's resistance to a change in its angular speed. So things that are already rotating want to keep rotating, and things that are not rotating want to stay not rotating unless there's some sort of an outside torque that's going to be applied to that object and change its rotational status. Again, the more massive something is, and the further away that mass is located from the axis of rotation, for example, if this was a wheel where most of the mass was located on the edge of the wheel rather than throughout the center, that thing would have a very large moment of inertia, making it more difficult to get this thing to start spinning or rotating. If the mass was much lighter and located very close to the axis of rotation, this object would be much easier to start spinning. Think of it as like trying to start a tire spinning versus starting to spin maybe a ring that would go on your finger. What we can now do is we can look at rotational kinetic energy in light of this new quantity of the moment of inertia, where kinetic energy can now be defined as a rotational kinetic energy being 1/2 I omega squared. Again, we're just coming back to this equation here, where rotational kinetic energy was the 1/2, the omega squared, and this big quantity as the summation, recognizing that that quantity really ends up being moment of inertia, which, by the way, is measured in units of kilogram meters squared. So although we call this 1/2 I omega squared rotational kinetic energy, it's not a new form of energy. It's still that same old kinetic energy. It's mass moving, but it's just sort of playing a new role in this case, where the mass is, rather than translating here, it's a rotational quantity. We can now recognize that a change in energy can include really both a change in translational and rotational kinetic energy. Something could be rotating and also translating. If you think of maybe a ball that is rolling across the ground, it's rolling and rotating, but it's also translating and moving across linearly as well. So we want to be able to recognize that motion can include both forms of kinetic energy. So remember, our equation for the moment of inertia is really a summation of these collection of particles. If you wanted the most general equation for the moment of inertia, it would be this summation of mr squared. But for an extended object that isn't just a collection of a few little bits of particles, but instead many, many, many particles that all might be a part of this big CD, again, that's rotating in some way, we need to be able to sum up all these little bits of mass for a big extended object. If we wanted to sum up all these bits of mass and look at an extended object instead, then our moment of inertia would be equal to this summation again, but of all the little tiny bits of mass, as those little bits of mass go to an infinitely small size. So if we sum them all up and get them to be infinitely small, we're really looking at an integral. And so another way to really look at the concept of moment of inertia is looking at it as the integral of r squared dm. Now notice that this integral has m as the variable of integration. Since it's usually easier to calculate I in terms of volume, how are mass and volume actually related? Again, the issue here is that we're trying to integrate an equation that is in terms of r, and yet the variable of integration is in terms of m. So there's a disconnect between our variable and our equation. So again, we want to look at a connection between those two. And of course, the answer is density. Density links mass and volume, so that if we were to look at a little bit of mass and a little bit of volume, we could solve for dm being rho dv. And rather than writing dm in the integral, we could write it instead as rho dv. This just gets us a little bit closer to having our variables match up. Now they don't match yet, but you would have to look at a given problem and the particular link between an r variable and a volume variable to rewrite those things and have them actually match up. If rho is constant, you could evaluate by pulling rho outside of the integral. But if rho is not constant, if this is not a uniform density, then you must know how that variable is going to change with position. Basically, you would need to know rho in terms of r and have an equation for that in order to actually evaluate that integral. What's nice is that if the object is symmetric and has uniform density, which many objects do, or we can at least assume that it is pretty close to that simplification, then there are some actual pretty simple equations that you can use to find the moment of inertia. So moment of inertia is something that you can actually look up in a table for a particular shape. If you see page 300 in your books, you'll be able to see some of those examples. Let's look at an example where we will find the moment of inertia and the rotational kinetic energy. Here we have 4 small spheres that are fastened to the corners of a frame, where the frame itself will have negligible mass, so we will not need to pay attention to the mass of the black rods connecting the masses. This thing will be lying in the xy plane, And the system's going to start out by rotating around the y-axis. If we were to look at where that y-axis is coming through, we're starting out with the y-axis coming through here, and the system rotating about this axis. We want to find the rotational kinetic energy and the moment of inertia of this system if it's rotating around this axis at some speed omega. Now let's start out by finding the moment of inertia, because in order to find rotational kinetic energy, we will need that value first. So let's start out by finding I. Remember, finding the rotational moment of inertia is going to be a summation of any bits of mass and the distance r of where they're located squared. So we're going to sum up all the bits of mass and where they are located relative to the axis. Now what we need to realize here is that these lowercase m's, these masses are right on the axis of rotation. So if we looked at the r distance away from the axis of rotation, it would be a 0, and those masses will not now add into our summation in any way. Instead, it's these capital M masses out here that are some distance away from the y-axis and would now sum into our finding of the moment of inertia. Here we would see that we would add up the big capital mass M and its distance away from the axis as a distance of a squared. Now we've taken care of this one, but there's another one over here, so we'll add in that mass as well. And we see that the moment of inertia of this system is simply a 2ma squared. If we wanted to find the rotational kinetic energy then of this system rotating about the y-axis, we would take 1/2 I omega squared, where we now know that I is equal to 2 capital M A squared. Our 2 and our 1/2 would cancel out, so that our final answer for the rotational kinetic energy would simply be capital M A squared omega squared. Now, what if we change this problem up just a little bit? And instead of having the system and the frame rotate about the y-axis, what if it was rotating about the z-axis instead? Now our axis of rotation is going to look a little bit different. We're now talking about an axis of rotation that's kind of coming in and out of the plane, a z-axis here, and we'll be rotating around this axis with that speed omega instead. In this case, we still have the rotational, that moment of inertia, or that rotational inertia, being the summation of all the mr squareds, but this time none of the masses are actually sitting on the axis of rotation. That means that the lowercase m's are going to add into this summation, in that we have this mass up here at a distance b away, and we have this mass down here at a distance b away from the axis. We also have big capital M at a distance a away from the axis of rotation, and this big capital M at a distance a away from the axis of rotation. Meaning that when we solve for the rotational inertia now, our total rotational inertia, or moment of inertia, is 2ma squared plus 2 lowercase m b squared. And when we put this into our equation for rotational kinetic energy, we again want to plug this I value into the equation, and we get 1/2 our I value multiplied by omega squared. Now you could simplify this down if you wanted to. The 2's and the halves could cancel out as well. But again, you kind of get this idea of summing up bits of mass at various locations away from a rotational axis.